Hello, I'm Kyle Francis,
And I'm Mohammad Bilal.
and our presentation is on electron microscopy. The Nobel Prize winner that we will be talking about is Ernst Ruska. He was awarded the Nobel Prize in 1986, and this was due to the fact that he and Max Knoll created the first electron microscope in 1931. Max Knoll did not receive a part of the Nobel Prize as he died in 1969, and it was only 50 years later when they actually received the Nobel Prize. In fact, Ernst died 2 years later after receiving the Nobel Prize. Microscopy is the field of viewing objects that cannot be seen with the unaided eye. At best, the human eye has a resolution limit of around zero point 0.1 millimeters, and microscopy generally relies on the principle of diffraction, reflection to increase resolution. Resolution is broadly defined as the ability to distinguish 2 points from each other. The light microscope revolutionized biology, as it allowed us to see into the world of cells. However, seeing anything smaller, such as viruses or nanoscale features, remained elusive to us, and this is because of the resolution limit of light. In 1873, Ernst Abbe made this relationship where the resolution is dependent on the wavelength and the aperture half angle of the microscope. In fact, theoretically, the highest resolution that you can get in a light microscope is half the incident wavelength. So in order to circumvent the resolution limit of light, electrons were used. And this is because of the de Broglie wavelength. In 1924, that he postulated that electrons have wave properties, and he actually won the Nobel Prize in Physics in 1929 for this discovery. So the de Broglie wavelength basically relates the momentum of the particle to its wavelength. Now, in the TEM column, we impart momentum to the electron by accelerating it through a potential drop, where the potential energy is equal to the kinetic energy. And this formula right here is basically a modified version of the E is equal to 1/2 mv squared. Now we can substitute this into the momentum formula to get this here, and then our wavelength becomes basically dependent on the electron energy that we imparted. And for electrons that have energy greater than 100 kilo electron volts, then we have to take into a relativistic effects. Now, I'm not going to do the calculation, but for example, 100 kilovolt electron is a 0.0037 nanometers, which is incredibly tiny. There are two types of electron microscopes that we use today. The first one is a scanning electron microscope, which is more accessible to the user, but offers less magnification. And then there's the transmission electron microscope, which is the TEM, which offers greater magnification, but sample preparation is a bit more tedious. In the EM column, this is where the magic happens. You can see on the figure on the left the differences between the TEM and the SEM, where once you make your electron beam, they go through a series of lenses, and for TEM, the beam is transmitted through. Here, the beam is parallel to the sample, and then afterwards is the detector. And then the SCM used to condense the lenses to focus the beam onto a point onto the sample, and the detectors are above. In SCM, there's the existence of scan coils that aren't in TEM, which basically move this beam across the sample pixel by pixel. However, in TEM, the whole image is generated at once. So these lenses, the condenser and the objective lenses, are solenoids that are basically, they use a magnetic field to focus the beam onto the sample, and then the objective lens either forms the final probe in the SEM or contains the image. And while these lenses are absolutely necessary, uh, all lenses have aberrations, which decreases the resolution. In the gun source, there are two types. There's thermionic emission and field emission. In thermionic emission, we heat the material enough where the electrons in it have sufficient energy to overcome the work function. The materials used is either tungsten or lanthanum hexaboride. And for the thermionic emission, we have a Wenhelt, which is a simple lens, and which basically is the first lens that focuses those electron beams. And then we have an anode plate that accelerates the electrons down the column. The second gun source is the field emission gun. Now, this is built on the property that electric fields are drastically increased at sharp points. So they use this very sharp tip that's 200 to 2000 angstroms thin, and then they use two anodes to extract those electrons, as these generate a second electron field. There are multiple interactions that electrons have with solids. You can produce auger electrons, secondary electrons, characteristic electrons, and they can also generate electron hole pairs and absorb electrons. However, the what we really care about in SCM are the backscattered electrons and the secondary electrons. When the sample is less than 100 nanometers, that's when we can actually start transmitting electrons through the sample. And here we get diffracted electrons as well as the scattered electrons. We can also get Bremsstrahlung X-rays. In SCM, the two main interactions we care about are scattering. It's either going to be where the electron's backscattered, when this is a elastic scattering, or the primary electron ejects a secondary electron. Note that the secondary electron will have drastically much less energy. Once the electron probe hits the sample, you will generate an interaction volume. The smaller your accelerating voltages, the smaller the interaction volume. While it may seem like more interaction volume is better, it's for the most part it's not true. More interaction volume means that you'll have more noise. And when it comes to secondary electrons, which are the primary electrons that we use to generate an image, they're only a few, nanometers deep, as these low energy electrons will not escape the bulk sample. When it comes to the backscattered electrons, these will have more energy to escape the sample, which is why they have a larger um, generation volume. When it comes to a secondary electron, those are more surface sensitive and offer better contrast, as you can see in this picture. However, when we switch to a backscattered electron, we lose some of that contrast, but we can see more of a contrast when it comes to different elements. Because when you have a higher atomic number Z, you'll increase backscattered electron. In TEM, you use both type of scattered electrons. However, instead of going pixel by pixel like in an SCM, the entire image is already generated, as you can see here. One important technique that you can do with the TEM is electron diffraction, as you can see on the figure on your right. However, the figure on the left may seem distracting, but one thing you should just get from this is the fact that we can switch from taking the selected area diffraction aperture in and out and choosing between a diffraction pattern and your image with basically a click of the button.
Alright, so why would we care about cryo-EM? So let's compare X-ray scattering with electron scattering. So as we know, electrons are negatively charged particles that interact better with matter because they're electron clouds in molecules. So the magnitude of the scattering is significantly larger, which is generally a good thing, but could be a bad thing as we'll discuss later. Second, electrons deposit less energy per useful diffraction. This is compared to X-ray, especially the high energy X-ray techniques like serial femtosecond crystallography and synchrotron radiation. So there's actually less damage. Third of all, resolution is higher in electron microscopy. This is due to the short wavelengths of the electrons. Finally, just like in neutron diffraction, with electron diffraction, we can find hydrogen atoms, which is not the case in X-rays. So let's remind ourselves of the concept of Ewell sphere, and it's an imaginary sphere with a radius of 1 over the wavelength. And the intersection between this sphere and points on the reciprocal lattice generates diffraction spots. So here from this figure, all I want y'all to notice is a change in angle from the 0 Orlawi zone as you see in the figure and the first Orlawi zone. It's a significant change in angle. This is going to be important in the next slide because the Ewell sphere of electrons is significantly larger because the wavelength is significantly shorter. So for all intents and purposes, the Ewell sphere is flat in electron diffraction. And basically, we can only measure the 0 Orlawi zone here in one image. Reaching the first Orlawi zone means that we need a very large angle that we cannot see on the detector. So compared to XRD, where we can see in one image multiple data from multiple Lawi zones. So this is going to be a problem in indexing, and of course we're going to try to tilt the crystal to collect data from as many planes as possible. However, we cannot have complete data if the crystal is not symmetric enough because we only have plus minus 70 degree rotation with the stage. So let's also compare with the aforementioned X-ray crystallography techniques. So this is a synchrotron, and this requires single crystal, which is large enough micrometer size, which we know that is a problem because we're not usually able to get crystals. So this is in addition to the limited resolution that is known for X-rays. So this is the other technique, serial femtosecond crystallography, which relies on X-ray free electron laser beams. They're short femtosecond time pulses that are shot on a jet of very small microcrystallites. So we can get thousands of images from those microcrystallites, but these microcrystallites will be destroyed because of the high brightness radiation. So we use these images to generate our crystal structure. But booking XFEL time is incredibly hard because there are only 2 in the US and just 7 in the entire world. So this is just in comparison. In Japan, Spring Gate synchrotron next to the XFEL, very huge, hard to maintain, and expensive to build. So what about microelectron diffraction then? In theory, we need only one or maybe a few nanocrystals, and we don't need the crystallization process because we can usually have these in crystalline solids. This technique is accessible, just like TEM. There's available at academic institutions, and plus the perks that we know about electron diffraction compared to XRD that we discussed earlier. So enter the 2017 Nobel Prize awarded to Jacques Dubochet, Joachim Frank, and Richard Henderson, who have worked on this technique since 1980s. So they're able to harness the power of electron microscopy and cryo to, first of all, protect the sample from vacuum in the TEM chamber. Second of all, they were able to protect the sample from electron beam damage because it's cooled down. So I'm going to talk about the third one, Richard Henderson, who was able to get the second ever structure of a membrane protein. They're very hard to crystallize, so in their native form. So this is bacteriorhodopsin, was able to fit a model in it, and we can see the amino acid residues and the retinal molecule in the center, and that was in 1990. Right now, after the detector caught up in about 2014, detector technology got very good, so we can use low doses. And we can see how this revolutionized the resolution of protein. So before 2013, this is what X-ray techniques was able to give us for glutamate dehydrogenase enzyme. And now using cryo-ED, we have atomic resolution. So this is how it works. We drop cast our solution on a carbon grid, and then we flash freeze it or vitrify in liquid ethane cooled by liquid nitrogen, and then we thin out the crystal so that it's transparent using gallium focused ion beam, and we acquire TEM data, we acquire the diffraction, and we do the indexing and phasing, which is the hardest part in electron diffraction. And then once we have the reflection file, we can use our favorite refinement technique to get this structure. So this is what a modern setup would look like. On the left is the fancy TEM with the specific capabilities. Thermal Scientific is pushing this technique really hard. And on the left is the sample preparation, the cryo-focused ion beam, so that we can create the perfect thickness, which brings us to how to and why we thin out the sample. So we have a crystal, we use gallium ions to get these nice images, and also to cut through those blue rectangular boxes to get it to the 150 to 300 nanometer thickness that is suitable for electron diffraction, because it's in the 0.5 to 2 times the mean free path of electrons, so it's transparent enough. So this is the important, want to highlight the importance of the sample thickness, because when it's too thick, we get bad resolution because we have bad data. But when it's here, I will show that. So this is the best cases. So we need high energy electron beam, and also we need the 0.5 to 1 mean free path thickness. And we see that we have more spots when we thin the sample, but we can see there's a lot of background. But on the other hand, when it's a little thicker, we can see that we have stronger spots and less background. So there's really a sweet spot when we have like significant layers of the unit cells, but as soon as the crystal is thin enough that it's transparent to electrons. So let's talk about the dose and beam damage, and this is how the diffraction intensity of those polymers fade with accumulated dose. And here, the take-home message is that we don't care about the rate of electron beams. So we all care about is the dose. So, and this is with temperature as we expect, using cryo and also preparing the sample with the absence of oxygen and water can give us better protection against beam damage. I want to also highlight that for certain functional groups, electrons can chemically react with them. So here the disulfide bridges are being reduced, and this is even at very low doses. So we have this big limitation in electron diffraction, and we need very, very good detectors to be able to detect at low doses. And finally, I want to talk about cryo-EG of small molecules. So basically, we have an organic compound that is solid and crystalline. We can put it on a grid, and then we can, in a few minutes, get a structure and also refine hydrogen atoms. So this is what it looks like from a powder, and we can get a crystal very quickly. And we can actually screen multiple organic compounds on the same grid. So this will have certain applications. Finally, I want to talk about certain potential use in metal clusters. So because electrons are very sensitive to the electronic environment of the molecules, we can see the change in oxidation state in electron density. So when we have a reduced state of a cluster, we can see that with electron diffraction. And finally, there aren't so many techniques in inorganic chemistry, but I guess that's the main take-home message. We need to make that happen. We need to find ways to use electron diffraction to solve problems in inorganic chemistry, which will open doors in front of us in the future. And all of us can be part of that. So thanks y'all for listening, and have a good day.